Hello, this is Dr. Johnson. I'm one of the AP Stats teachers at Capel High School. Welcome to this video on quantitative data describing with numbers. Today we're going to talk about three different measures of central tendency. The mode. The mode is the value that occurs most frequently. You can see it in that graph right there. It is the highest point, the point that has the most frequency. The median. The median is the middle value when the numbers are arranged in increasing or decreasing order, so that 50% of the data is on the right side and 50% of the data is on the left side. And the mean or average, the sum of the values in a set divided by the number of values in the set. It's often thought of as the balance point in the distribution. The mode, let's talk first about the mode. Mode is the value or set of values that occurs most frequently in a distribution. If all values occur only once, there is no mode. With mode, think most. Most. We're trying to find the value that occurs most often, most frequently. So in this set right here, what is the mode? Well, I have 3/8 in that distribution, so the mode is 8. Easy enough to calculate. If the distribution is continuous, like this one right here, the mode is the point at that where the distribution reaches its maximum. And in the case of a normal distribution, the mean, median, and mode are all the same value. Mode. Now, modes can be more than, there can be more than one mode in a data set, such as bimodal or multimodal distributions. An example of a bimodal distribution is the price of books in a bookstore. You've got some books, the lower priced books will be the paperback books, and the higher priced books will be the hardback books. So if you take all the books together and graph their prices, you might have a bimodal distribution like that. A multimodal distribution, well, what's an example of a multimodal distribution? An example might be the arrival time of people at a restaurant. So there's a morning rush, a lunchtime rush, and a dinner rush. Now, one thing I want to caution you about when deciding when counting the number of modes is that you want to paint with a very broad paintbrush. When you look at a distribution, of course, because of random distribution, you're going to see some ups and downs, little ups and downs here and there, and that's normal. That happens. You should count something as being a separate mode only if it is a large distance from the other mode. So, think of painting with a very large brush. If you can get your big fat paintbrush, your roller brush, in between those two modes, then you can call them separate modes. Think of maybe if the modes are like one standard deviation apart, then they're definitely separate modes. So I want you to ignore the small little random variations in the distribution. Only count the big differences, the big modes. And here I have an approximately uniform distribution. It has no prominent peaks and no modes. Now, there are some drawbacks. The mode has some definite drawbacks. The mode is not necessarily in the center. Suppose I have a bunch of students who've taken the test, and several of the students have not taken their test. So I've given zeros to the students who haven't taken the test. And here's my dot plot of test scores. You can see that most of the students have taken the test, but there are 6 students who have not. The mode is actually 0 in this case, and that's nowhere near the center of this distribution. Also, another drawback to the mode is that it cannot be treated algebraically. You don't find a formula with the mode in that formula. So there are some severe drawbacks to the mode. It's hardly considered a measure of center at all. So we're going to move on to the next one. A median. A median is defined as the middle value when the numbers are arranged in increasing or decreasing order. Graphically, it is the point that divides the area of density curve in half. When you think median, think middle. We're trying to find the middle term. If there is an odd number of items in the set, it is the single middle value. If there's an even number of values in the set, it is the average of the 2 middle values. Example, suppose I have these numbers right here in example 1, what is the median? Well, the first thing you have to do when calculating the median is arrange them in increasing or decreasing order. Then you find the middle term. In example 1, it is 40. Example 2, I've got an even number of objects. So I have to, again, arrange them in order. Since it's an even number, I have to take as my median the average of the two middle terms. Example 3, I have the same as one as before. I have these 5 numbers. The median is 40. That's the middle value. For symmetric distributions, the median and the mean are equal. For symmetric distributions, the median and the mean are equal. The converse is not necessarily true. If the mean and the median are equal, from that you can't conclude that it is symmetric. What happens if the largest item increases from 42 to 242? What happens to the median? Well, that number 40 is still sitting there right in the middle. So we say the median is resistant or robust because outliers do not have a great effect on the value of the median. It will remain at the center. When there are outliers, the median is a better indicator of central tendency than the mean. That's important. When there are outliers, the median is the better indicator of central tendency than the mean. So if you conclude that there are outliers, I want you to use the median as a basis for comparing two distributions. If the distribution is symmetric, then you can use the mean. Another drawback of the median is that it, again, cannot be treated algebraically. You don't see formulas with the median embedded in that formula. Okay, now we go to, whoops, I skipped a slide. 10, where am I at? Mean. So now we're going to talk about the mean or the average. Sometimes it's also called the expected value, and first thing I want you to understand here is that we have to be very sensitive to notation. If we are talking about the mean of a population, we need to use the Greek letter mu. If we're talking about the mean of a sample, we're going to use x bar. You're going to see this come up again. If we're describing the characteristic of a population, we are going to use Greek letters. The mean is the value obtained by adding all the data values together and dividing by the total number, and I give you the formula right there. That's the formula. You can think of the mean as the balance point in the distribution. That is, if the distribution is made of some uniform solid steel, some uniform solid metal, then the mean represents the balance point. And if I were to take that little point out there on the right and extend it even further to the right, well, the mean would also have to shift. The balance point would also have to shift to the right. So you can see from this graphic here that the mean is going to be sensitive to outliers. So we say this: the mean is considered non-resistant or non-robust because it is influenced by outliers. This means that outliers and skewness can significantly alter the mean. The mean is non-resistant. That's a statistical term. You need to use that term carefully. An outlier is an individual observation that falls outside the overall pattern. In a short while, I will describe a mathematical way of identifying outliers. Distribution. A distribution is symmetric if the right half is the mirror image of the left half. Okay? Yes. Symmetric does not mean approximately symmetric. Use the term symmetric only if they are exact mirror images. If they are not exact mirror images but look pretty similar, then use the term approximately symmetrical. If the distribution is symmetric, the mean and the median are equal, though the converse is not true. Here I have a symmetric distribution of student male heights at Capel High School. It's symmetric, so therefore the mean and the median are equal. Skewness. Now, I have a graph here of showing skewness. The graph on the left is negatively skewed, or more commonly we will say that it is skewed to the left. If the distribution has a broad tail to the left, it is left skewed. If the distribution has a broad tail to the right, as in the right graph, it is right skewed. So in the let's go to the left graph. That's the negatively skewed, or the left skewed one. On the left graph, the mode again is at the top because that has the highest frequency. The median is a little bit to its left, and the mean is further to the left. We say that the mean gets pulled in the direction of the skewness. So the left graph is skewed to the left, and so we say that the mean gets pulled to the left. On the right, I have a right skewed graph. The mean gets pulled to the right. Now here I have a graph that is going to show you that. I want to demonstrate to you how the mean gets pulled in the direction of the skewness. Note that I have 9 boxes on each side. Since I have 9 boxes on each side, the median is 9. Now what I'm going to do is I'm going to rearrange these boxes. I'm going to move some of the boxes on the right a little bit more to the right, but I'm going to keep them on the right side. Boxes on the left, I'm going to move to the right, but I'm again keep those on the right side. So I'm going to keep the same number of boxes on each side, which means the median will not change. Okay? I still have 9 boxes on each side, so the median stays the same. 9 boxes on each side, so the median stays the same. 9 boxes on each side, so the median stays the same. But because now the distribution is skewed to the right, the mean is greater than the median. So if the mean is greater than the median, that suggests we have something that is skewed to the right. If the mean is less than the median, then we have something that is skewed to the left. Skewness. If the right tail is longer and broader than the left tail, we say that the distribution is skewed to the right, or positively skewed, and the median is less than the mean. Here, another way of describing it is saying that the mean of the skewed distribution is pulled toward the long tail more than the median. An example would be starting salaries of college graduates. Salaries tends to be right skewed. If the left tail is longer and broader to the left, the distribution is skewed to the left, and often the mean is less than the median. We say the mean is pulled in the direction of the long tail. An example is grade point averages or golf scores. Recapping. The mean is sensitive to outliers. It is non-resistant. That's the term we want you to use when we describe this. The mean is sensitive to outliers. It is non-resistant. The median is not affected much by outliers. It is considered resistant. It remains at the center. In a symmetrical distribution, the mean and the median are equal, but the converse is not true. In a symmetrical distribution, you should always report the mean. When the distribution is skewed to the right, it is likely that the median is less than the mean. If left skewed, it is likely that the median is more than the mean. If the mean and the median are significantly different, the distribution is unlikely to be symmetric. In an asymmetrical distribution, the median should be reported as your measure of center. And I wanted to just alert you to some of the extensions that we've seen on the AP exam. One year, they asked about a simple moving average. A simple moving average, it takes the last 3 points, divides them, last 4 points, divides them by 4. There was a year in which they talked about the mid-range formula. That is, you take the minimum and the maximum and divide it by 2. Okay. One thing they haven't talked about yet is the trimmed mean or truncated mean. This might come up, you never know. At a 10% trim mean, that's one discards the lowest and the highest 10%. And So effectively, that's one way of reducing the impact of outliers. Now we're going to talk about measures of dispersion. Measures of dispersion. The purpose of measures of dispersion is to describe the spread of the data, that is, how much it varies around a central value. First one we're going to talk about is the range. The range. The range is defined as a single number, that is the difference between the largest and the smallest values. It is a crude measure. It is sensitive to outliers. In fact, the range is totally reliant on the extreme values, and so it is very sensitive to outliers. That means the range is not resistant to the influence of outliers. Here I have three different distributions, and you can see that the first two distributions have the very same range, but I have to say you can't really say that the first two distributions have the same spread. There's quite a bit of difference. And one weakness of the range is that it only uses the extreme values for its calculation and really ignores how spread apart the data is in between. So the first two data sets have the same range, that is 50, but very different distributions. That's the one weakness of the range. So we don't talk much about the range. It's not one of our preferred measures of spread. We prefer talking about standard deviation and variance. Now, let's get some notation straight. Again, if we're talking about the standard deviation of a population, we're going to use a Greek letter, the Greek letter sigma. If we're talking about the variance of a population, we're going to use sigma squared. If we're talking about the standard deviation of a sample, then we use the symbol S. And for the variance of a sample is S squared. How do you interpret standard deviation? Put a star on this. This thing will come back to you over and over again this year. Standard deviation measures the typical distance between the mean and the values in a distribution. It is the typical distance. Maybe some people might say it is the average distance between the mean and the values in the distribution, but I think the more common word is to say it is the typical distance between the mean and the values in the distribution. Example, I have the height of male students at Capel High School is the height of the male students at Capel High School typically varies by 3 inches from a mean of 70. This is a interpretation of the standard deviation of male students at Capel High School. The height typically varies by 3 inches from the mean. So we have the phrase typically vary, then I have my standard deviation, and what does it typically vary from? It varies from the mean of 70. So which of the following data sets has the smallest standard deviation, A, B, or C? Which of the following data sets has the smallest standard deviation? You can see that these distributions are pretty similar. They just have increasing number of 3's. Which has the smallest standard deviation? Well, when I add a number that is less than 1 standard deviation from the mean, the typical distance between the mean and the values of the distribution decreases. So C has the smallest standard deviation. What are the formulas? Here's the formula for population variance, and there's the formula for sample variance. Okay, population variance uses the Greek letter, sample variance uses the letter S squared. Now you're looking at these and you're saying, well, Dr. Johnson, there's a difference here. In the population variance, we divide by n, the population size, and in sample variance, we divide by small n minus 1. That's the sample size minus 1. And you may be wondering, why do we do that? Why is that different? Well, we divide by n minus 1 so that we get an unbiased estimator, so that our sample variance, S squared, is an unbiased estimator of the population variance. And we'll talk about this more later. Here's my formula for variance. That upper formula is quite compact. This is my formula for sample variance. The upper formula, the formula for sample variance in the middle there is quite compact. If I want to spread it out, that's what it looks like. To get the standard deviations, all I do is I take the square root. The standard deviation is the square root of the variances that we had on the previous page. Here again is another way of, these are the same formulas, just written out slightly different. If this slide works better for you than the previous two, then use this slide. You'll have access to these slides in Schoology, so you can come back and look at this. 34. So suppose I want to calculate the variance and standard deviation from the following set. The numbers are 14, 13, so on. If it is not stated whether a data set constitutes a population or a sample, I want you to assume that it is a population. So what I have here is the data set is labeled as the ages of the 10 people in the room. If the data set is labeled as the ages of the 10 people in the room, I want you to assume that this is the population. We're talking a population of 10 people in the room. It's not interpreted as a sample. Something like that is referred to as a population. So here's how I do it. Here's how I calculate this population data. And when we ask you to show your work, this is what we're kind of expecting. I've color-coded things to make it a little bit easier. So population data, that's the same data, I've just color-coded it. The mean, I take all those numbers and I add them up and divide by 7, so I get 17 units, that's my mean. Now my population standard deviation, my mu, that's 17. So what I actually do, to do the write-up, I have something like this. I'm going to take all the summation parts of it. I'm going to take my 14 and I'm going to subtract 17. I'm going to square that. Then I'm going to take the 13. I'm going to subtract 17. I'm going to square that. And the 20 minus 17 and square that. So I'm just, for each number in my data set, I'm subtracting the mean and squaring it. And then I add it all up together. I get an 80. So the variance is going to be my 80 divided by 7, the number of data points I have. And of course, when you have variance, the unit is the units squared. So you have to include units. That gives context to your problem, to your answer. And to get the square root, you just take the square root. So the standard deviation, the population standard deviation is 3.38 units. The data typically varies by 3.38 units from the mean of 17. When we ask you to show your work, I would expect see that column of numbers in blue, brown, green. I expect you to show me the first one plus the last one. Okay, and then you don't have to write out all of them. You can do the first one and the last one, and between it put plus ... plus. Properties of standard deviation. Standard deviation measures the typical distance of the values in the distribution from the mean. An observation becomes as the observations become more spread out about the mean, the standard deviation increases. Standard deviation can be 0 or a positive number. It is 0 only if there is no variability, that is, all the observations have the same value. Otherwise, the standard deviation is greater than 0. Standard deviation and variance are sensitive to outliers. That means they are not resistant to the influence of outliers or extreme values. Standard deviation is measured in the same units as the variable, and variance is measured in the square of the variable's units. You'll have access to this slide deck, so you can come back to this. Interquartile range, that's our next measure of spread. Percentile. So to teach you about interquartile range, we first have to talk about its percentile. The pth percentile is defined as the value such that p% of the observations are less than or equal to it. That's the definition of the pth percentile. So under this definition, it is possible to have some score that is at the 100th percentile. That's possible with this definition. For example, a test score at the 95th percentile is greater than or equal to 95% of the other scores. Quartiles. To calculate the interquartile range, we have to calculate quartiles. The first quartile, sometimes referred to as Q1, or the lower quartile, is at the 25th percentile. So 25% are below, 75% are above. The median is sometimes referred to as Q2. That's at the 50th percentile, and that's in the middle, with half the values on either side. The third quartile is sometimes called Q3, or the upper quartile. It is at the 75th percentile. To calculate quartiles, I have it here in great detail. You don't have to worry about this so much because your calculator will do all the work. In a separate video, I will show you how the calculator will do that work. But here's all my data in order. To calculate my median, that's because I have an odd number of objects, odd number in my data set. The median is the middle term. Then to calculate the first quarter, the first quartile can be seen as the median of the lower half. So the first quartile would be 23 in this data set. And my third quartile, that's the median of the upper half, my third quartile would be 43. Okay, this slide right here gives you more detail on how to calculate that interquartile range. If you want, you can come back to this slide. The interquartile range is the range between Q3 and Q1. It is a single number. Interquartile range is Q3 minus Q1. And here I have an example. Let's say here, this is my data right here. The lower half is on the left, the upper half is on the right. Since I have an even number of data points, my median is the average of the middle two. Then on the first quartile is the median of the lower half, that's 64. The third quartile is the median of the upper half, that's 77. So my interquartile range is 77 minus 64, or 13. Okay. Interquartile range and standard deviation. The mean and the standard deviation are sensitive to outliers. They can be changed a lot by a few outliers. Generally, use the mean and standard deviation when describing a distribution that is roughly symmetric. The median and the interquartile range are not sensitive to outliers. This means they are resistant to the influence of outliers. Use the median and the interquartile range when the distribution is skewed. An extreme observation is called an outlier if it is less than Q1 minus 1.5 times IQR, or greater than Q3 plus 1.5 IQR. These are two formulas that are not on your formula sheet that you will have available on the AP exam. So you do have to memorize these formulas. The formula for a low outlier is any number that is less than Q1 minus 1.5 times IQR. And the formula for a high number is any number that is greater than Q3 plus 1.5 times IQR. In other words, an observation is an outlier if it falls more than 1.5 IQRs below the first quartile or more than 1.5 IQRs above the third quartile. Oftentimes when creating box plots, we use something called a 5-number summary. So, and your calculator will give you these numbers, and I'll show you that later. This is the 5-number summary. It consists of the following numbers written from smallest to largest: the minimum, the lower quartile, the median, the upper quartile, or the maximum. Okay? This right here is a box plot, or sometimes called a box and whisker plot. All you need to calculate this is the 5-number the summary, that is the minimum first quartile, median, third quartile, max. How do you create this? Well, the middle box extends from the first quartile, from the lower quartile to the upper quartile. And somewhere in there is the median. So that's the middle box. It extends from the lower quartile, 1Q, to the upper quartile, Q3. And somewhere in there is the median. You draw a line with the median. Now, the endpoints, the whiskers, go from the lower quartile to the lowest value, and it goes from the upper quartile to the highest value. This is a box and whisker plot. Well, this is a box and whisker plot if there are no outliers. I should be more specific. When you draw a box and whisker plot, I want you to label the minimum, the maximum, Q1, Q3, and the median. Put those labels in your graph. In box plot, the whiskers only extend to the smallest and largest points that are not outliers. The box plot extends to the smallest and largest points that are not outliers. Outliers are indicated separately, often with an asterisk. Now, if you look at this graph, let's say we look at January. This is temperature in Southampton weather station. I look at the box plot for January, and I see that the maximum is somewhere around 11, and the minimum, well, there's a little dot way down there by 1, but that was an outlier. The whisker only extends from the first quartile down to the lowest point that is not an outlier. The outlier is represented separately by a circle. Oftentimes we represent outliers by little stars, little asterisks. The February data has no outliers, the March data has no outliers, but the April data again has an outlier. Now, one thing nice about box plots is that they can be used to compare different distributions, so we can ask lots of questions about the distributions of temperatures in February versus April. Which one had a wider distribution, which one had higher median, that kind of stuff. Extensions. These are extensions that, have come up in the past that on former AP exams. The 90-10 percentile range, instead of using the interquartile range, what if you use the 90-10 percentile range? That's the difference between the 90th and the 10th percentile. There was one year where they asked about measures of skewness, and they had you calculate the mean divided by the median and ask you questions about what would, if the mean over the median is greater than 1, what does that say about skewness? Transformations, we're getting to the last part of this slide, but this is also very important. What happens to the center shape and spread of a distribution if the original values are adjusted in a particular way? So, first of all, what happens if the original values are adjusted in a particular way? Suppose that I add a constant to all the values in the original distribution. Adding a constant shifts the center of the distribution by that amount. Okay? Adding a constant shifts that distribution, the center of that distribution, by that amount. In fact, it shifts all locations in that distribution by that same amount. So here's my graph. If I take my original distribution and I add the value A, I get my transformed distribution. Well, the mean of the transformed distribution will be A greater than the mean of the original. The first quartile of the transformed distribution will be A greater than the first quartile of the original. Here's the formulas that represent that. If I add a constant A to the original values, that shifts the center of the distribution by that amount. So the mean of the new distribution of x plus A is equal to the old mean plus the constant A. Now, adding a constant does not change the spread. It doesn't change the range, the IQR, the standard deviation, or the variance. So I can write the standard deviation of the new distribution is equal to the standard deviation of the old, and the variance of the new distribution is equal to the variance of the old. And again, it doesn't change the shape. If you start with a normal distribution or a uniform distribution and you add a constant, you'll still get the same. What happens if the original values are adjusted by multiplying all of the values in the original value? What if I multiply all the original values by a constant? This multiplies the mean by that very same constant. So let me show you in this better graph right here. So my original distribution is that 1 in the middle. And if I multiply all the values in that original distribution by a constant greater than 1, well, that's going to spread out that distribution. It's going to get broader, and the center is going to increase by a factor of b. Now, if I take that original distribution and multiply it by a constant less than 1, then the distribution is going to get smaller. It's going to get more narrow, it's going to get taller, and the mean will also decrease. I'm assuming here that b is some number greater than 0. So in math, in symbol terms, this is what's happening. If you multiply all the original values by a constant b, that multiplies the measure of center, the mean and the median, by that same constant. So the mean of the new distribution, bx, is equal to b times the mean of x. It also multiplies the spread, whether it be the IQR, range, or standard deviation, by that same constant. So the standard deviation of the variable bx, that's the transform variable, is equal to the absolute value of the standard deviation of x. However, the variance of the transform variable bx is equal to b squared times the variance of x. I'm going to go back to standard deviation. The standard deviation of the transformed variable bx is equal to the absolute value of b times the standard deviation of x. Why do you suppose it's important that b is greater than 0? Well, because standard deviation is always positive. So the standard deviation of bx has to be a positive number. So that's why we have that absolute value sign there. Here's some testing suggestions. We'll get back to those later. Testing suggestions. I want to talk about this, how to compare two distributions. Suppose that I have back-to-back stem plots showing the number of home runs that Roger Maris hit, number of home runs that Babe Ruth hit. Of course, you have to have a key. That's saying the key is telling me that 335 means that 33 home runs were hit by Roger Maris and 35 for Babe Ruth. All this is based on this 5-number summary right here. So I know my median, I know my max, I know this data right here. Here's how I want you to answer these. The center. We start out with a opening sentence that summarizes the conclusion about the center. Babe Ruth tended to hit more home runs than Roger Maris. How do I get that? Let me go back. Babe Ruth tended to hit more home runs than Roger Maris. The mean, and here I have to have some calculations to show it, of Babe Ruth at 43.9 home runs is greater than that of Roger Maris at 26.1. So I actually am using the mean and standard deviation here because these two distributions are approximately symmetric. So I'm going to compare means, and I say the mean of Babe Ruth, and I have to give its value, is greater than that of Roger Maris, and I give its value. Notice I use the word greater here. Greater is one of those comparative words. If you're comparing two distributions, you have to have a word of comparison, and greater is a good one. Unusual feature, Roger Maris has an outlier. I have to show the work to do that, and Babe Ruth has no outliers. Spread, the population standard deviation of Maris at 14.8 home runs is larger than Babe Ruth at 10.9 home runs. So for this, I have to do some calculations. I'm going to show my work elsewhere. And I have my word of comparison, larger. I have the two values right there. Shape. Babe Ruth's distribution is slightly skewed And here I can, to demonstrate that, I might show that how the mean compares to the median. However, Roger Maris's distribution is skewed to the right, and then to support that, I would show that his population mean is greater than the median. So that's a model answer. It compares the centers of the two distributions, the unusual features, the spread of the two distributions, the shape of the two distributions. For each of these, it gives you particular values. It has words of comparison. This is a model answer, and this is what we'll expect to see on your exam. That's it for today. Thank you very much.